I'd like to welcome back for his second visit to Gippstech, David VK5DGR. And he's going to tell us about the next step on with FreeDV. Welcome, David.
Thank you. Okay, today I'd like to talk about the SM2000 VHF digital voice radio that I've been working on with a team of hands for about the last 6 months. I'd like to start by talking about the FreeDV, what is FreeDV, and talk a little bit about the SM2000. Then we'll talk about some new digital voice modes that we've developed called FreeDV 2400 A and B. And then lead into why we need to build the SM2000, why we need to build a custom radio instead of using what's off the shelf. Where we're at in the development, a status, and a little bit of a demonstration. We have one running out the front here. Okay, so what is FreeDV? Until recently, it's basically open source digital voice for HF radio. It consists of a codec 2, which I developed, a modem designed for HF, the HF channel, in particular digital voice over HF. It's got a little bit of forward error correction, and to run FreeDV, you can use a GUI application that you can download for Windows or Linux or the Mac. It also comes in a software library form. It's completely open source, so you can just take some open source software in the form of an API or C library and integrate it with your SDR project. And I get emails every week from people who have integrated it into their homebrew SDR radios. You can also run it with the SM2000 FreeDV adapter, which I'll just start passing around the crowd. You've seen one, I think. Yep.
You've got one at home.
Which a few of you have already. There's been some other developments. There's a FreeDV beacon in Sunbury, just outside of Melbourne. You can, it's an automated Raspberry Pi that talks FreeDV and will record your FreeDV signal and send it back to you. There's also a weekly WA rebroadcast from the ARED Club in Adelaide, 7.177 between 9 and 10 a.m. Sunday mornings. Good chance to have a listen to some FreeDV and
South Australian time.
South Australian time, yeah. Is there another one?
That's the problem. You can sleep in.
Yes.
Change that to 10 a.m. or we go starting at 10 a.m. now, not starting at 9 a.m.
That's right, from 9 to 10 a.m. There's some debate. When we do the broadcast at 9 a.m. we can't hear it in VK5, it's only VK3 if you come back to us on 40. So in order that we can hear it locally, we're thinking of changing it at 10 a.m. So it's moving around a bit at the moment. More information on the ARED website. This is one of the ways you can run it. This is a screenshot of the FreeDV GUI program. So you get things like, that's the spectrum of the HF FreeDV signal, some modem information in the scatter diagram here, and a few statistics like signal to noise ratio, your bit error rate. And you've got, it hooks up to your radio via a rig interface, and you've got your PTP and all sorts of other gadgets you can press in various different modes that are supported. So that's one way you can run it on HF. So the FreeDV GUI application combines the HF modem and codec 2, runs on a bunch of different operating systems, and pretty much allows any SSB radio to be used for digital voice. You don't need any special new radio or anything like that. We've got people running this on 50-year-old valve radios quite happily. In the last 3 years it's become pretty popular in the ham radio community. When there's a good signal, about 10 dB signal to noise ratio, it's noise free, which is unusual for HF. Not quite as robust as SSB, it will fall over if you get too much fading and things, but we're working on that. There's some ongoing work to improve the HF modes. Okay, there's also the SM2000 Smart Mic, which I've started passing around the room, the little blue box. That's embedded FreeDV, so you don't need a PC. It's sort of a microphone form factor, has a built-in microphone and speaker, runs off battery power if you want to, and turns any SSB or FM radio into a digital voice radio. It's got built-in rig interfaces, transformer coupled and opto coupled for push to talk, and a built-in microphone and speaker. So that can plug with your own cables that you hook up to your particular rig, then you can do digital voice without a PC. And they're around $200. And we released those about a year ago. And there's 300 or 400 floating around at the moment. that's what it looks like, and that's what's being passed around the crowd. So a microphone, speaker, a few little trimmers to adjust for your particular rig, all the levels, and a bunch of ports for cables and an RJ45, so look up to those rigs that have RJ45 plus DC power. So that's the whole thing in an embedded box. And that was developed by several hams around the world. And some of the technology we use in that, particularly the microcontroller and experience I guess we got from that, we put into this next project. Okay, so we've got a fair bit of experience over the last 3 years with HF digital voice and a wide range of software and hardware implementations, and quite a few people using it around the world. In late 2014, we started looking at the current batch of modems for data and digital speech. And what I found, just by doing some sort of computer simulations of these modems, were a lot of these modems weren't very good. A lot of bits were being left on the floor. What I mean by that is that due to the design of the modem waveforms and the implementation of the modems, we were wasting a lot of power that was being used to send both data and digital voice over the VHF radio. I have a background in satellite communication where every fraction of a dB counted. If we built a modem and it wasn't non-theoretical, within a 0.2 of a dB, we'd get sent back to do it again. So I nearly fell over when I found that some of these modems were losing 7, 8, even 10 dB, what we call implementation loss of the modem. So I wondered what could be done about this to improve the situation. I found one of the main reasons was in the demodulator and radio design. We did some initial tests, which I spoke about in last year's talk here. We demonstrated gains of up to 10 dB over analog FM. Now that was done using things like SDR dongles and other bits and pieces that were sort of cobbled together. So now we'd like to push that a little bit further. So just talking a little bit about what modems do. The idea is that you put bits in one end and they convert it to some sort of analog waveform that can then be sent over a radio channel. The channels add noise, sometimes add other impairments such as frequency offsets, fading can be a problem, and then bits come out. A good modem can handle a lot of noise and very weak signals. A bad modem, not so well. And the way we characterise this is in terms of bit error rate. A given amount of power, how many errors go over that channel and come through as errors or the wrong bits. So why does it matter if the modem is good? Well, it turns out that the difference between a bad modem and a good modem can be up to a factor of 10 or 10 dB. That gives you a lot of advantages. For example, you can have less power, both in terms of battery power required for a portable application and transmit power. That can extend to advantages in battery power. Also in things like less interference. A lot of the problems these days with, in particular in commercial applications, with channel spacing getting smaller, the amount you transmit into adjacent channels, say through phase noise of your transmitter or other spurious emissions, that's reduced if you don't have to transmit as much power. There's also hardware costs. It costs a lot less to make an amplifier that's 10% of the power output of another one. And longer range if you use the same power. Something else you can do if you've got a larger system gain is you can trade off that power for bandwidth. So you can have 10 times the bandwidth at the same power. Or you can have the same bandwidth as in bitrate with 1/10 of the power. So there's opportunities with the same power output we've got now to have higher bit rates over the channel, which means faster data or maybe higher quality speech. So, good and bad design. Just about everything we do these days uses this design. It's always assumed we've got an FM radio with an FM demodulator, and then we feed it into some sort of digital demodulator and a codec. That's how your APRS works. That's how all the C4FM, D-Star, DMR work. They always assume this analog FM radio architecture. No, not anymore. This is the way you build a much better system, and this is the cause of a lot of the system losses, if you like. So, we've developed recently a couple of new modes called FreeDV 2400A and 2400B. They both use codec 2 at 1300 bits per second. Now that's the bit rate we've been using over HF for the last 2 or 3 years. It's not wonderful quality speech. I'd say it's sub-FM, but it's good enough. People are using it over HF quite happily. It gets the message through, so we've used that as a starting point. That's then expanded out to 2400 bits per second over the channel. by adding some synchronisation and protocol bits. And there's also a few spare bits, which I'll talk about in a little while. There's two modes. 2400B is designed for high performance. It uses 4 FSKs, so frequency shift keying with 4 different tone frequencies. And you need an SDR modem, or a modem implemented on an SDR to use it. 2400B can pass through any FM radio, even a $40 HT with average performance. So basically, 2400B is this one that I've said no to, but we're doing anyway. And 2400A is this one. The difference with this one is with 2400B is you don't need a modem with a data port. It'll run over a $40 power thing, and we've demonstrated just that. So we thought that was significant enough to give it a go, even though it uses the dreadful FM demodulator architecture. Okay, so now I'll try and play a demo through some speakers here. So this is from some initial work that Brady, who's sitting in the audience here, waving his hand there, did about 6 months ago, where he developed the waveforms, and we just simulated it in this case. It's a simulation of what FM and the 2400A mode sound like at the same signal-to-noise ratio. Actually, was this simulated, Brady, or off the air?
That was on the air.
This was off the air, that's right. Brady went mobile in his car, and at the same location, sampled 2 signals. So first the FM. I'm just going to hold the little speaker up to the microphone here. And now FreeDV 2400A.
This is Brady Brand, HC9 Kilo Charlie 9, Tango Papa Alpha, testing FreeDV, the VHF SDR and 2400B.
Okay, so you can see that we're kind of right on the edge there. We did that on purpose. We wanted to get right to the edge of FM and then see where we were standing with the 2400A. 2400A, quite intelligible, understandable, a bit mechanical and robotic, but that's the nature of the codec at that bit rate, but still very much more usable than FM at the same receiver input. Now this plot shows why. This is a spectrogram, so we've got time going across here. And what we're doing is alternating FreeDV 2400A with the FM signal. Now the FreeDV 2400A signal is much narrower. So all that power, the power we've got available from the transmitter is put into a smaller RF bandwidth, which means it has a much better job of picking it up. But the demodulator, the FM is spread over a much wider area, so it's sucking up a lot more noise at the same time, and that impacts on how well we can do in demodulating it. So that's 2400A, 2400A, FM, FM. So that's just a plot of the signal at the input to the demodulator. Okay, so a little bit about the 2400A waveform. 2400 bits per second, about 5 kilohertz of RF bandwidth, which means it would fit in 6.25 kilohertz channel spacing, which is kind of what industry is driving on for VHF two-way radio. It uses 4 FSK modulation, so frequency shift keying with 4 separate tone frequencies. It's something called non-coherent detection, which pretty much means we just filter and average the signal for each tone over a single period. It sends 1200 symbols per second. Now each symbol is one of those 4 tones. So 1200 times a second will swap what tone we're sending over the channel, and the tones are spaced at 1200 hertz. The frames are 40 milliseconds long, and each frame is 96 bits. We have 28 bits per second frames spare for routing, text, or expansion. We decided just not to allocate them at this point because we're really interested in seeing what we can do with the digital voice by itself. Other people can come up with how they want to route it and put it through the repeaters, or send other data if they want to. The downside, I guess, is it's not going to run on most of your current radios. You need an SDR radio to reach the performance goals. In particular, it won't run on legacy FM radios, even those with data ports. The other way to do this is use an SSB radio and move your signal up and down to RF using an SSB radio connected to a PC. Can't do that because it's too wide for SSB radios. We need the full 5 kilohertz. It's a complete departure from FM-friendly VHF, UHF digital voice that everyone else is doing at the moment. And that's on purpose. The current, as I've illustrated, the current FM demodulator architecture that cause big performance drops, and we can do a lot better than that. So it's designed without compromise in the mode and the radio to explore new ground, rather than saying, oh, we've got a bunch of old radios, how can we reuse them? So no apologies for that. And it's completely open source, including the codec. No lockdown, no licenses, quite free to experiment. So this brings us to, I guess, why we needed the SM2000. So where we're at, I guess we have an open source codec, growing experience with modems. As I said, the FreeDV 2500A waveform is 5 kHz wide, so we can't run it on any of our existing kit. Also, the 10 dB gain, it does seem a bit too good to be true. It's a long way ahead of a lot of other radios that are out there. So I felt that we needed hardware to support these new waveforms and demonstrate what we can do with open source VHF digital voice. So I decided to build the radio to go with it. So the SM2000, we've got one up here, but this is the printed circuit board for it, which that's just a blank run of the prototype. I'll pass around. It's open source hardware and software, so we've published all the design. It's available up there on SVN if any of you would like to have a look at it. Circuit, printed circuit board, even the bill of materials and parts list with DigiKey part numbers is up there in open source hardware. All the software's open source as well, up in SourceForge that you can download and have a look at. So the whole thing, right through the antenna to the speaker, electromagnetic to acoustic waves, all open. No lockdown, everything's there for you to play with, experiment, or add to if you like. I have 3 specific goals to start off with. We want to show that it's possible to make a complete radio that's open source, both hardware and software. I'd like to demonstrate this 10 dB minimum detectable signal that's lower than the existing FM and first generation, what I call first generation DV systems, which is all the DV systems that are out there at the moment. And a couple of other goals that I'd like to look at is wideband audio. What if it's possible to put, say, higher quality audio, not just 3 kHz audio through this thing, like AM radio, Skype quality through our VHF or UHF radios. That's possible now. We've got control of the codec, the modem, and the hardware. So we can start thinking about those sort of goals. Relatively broadband data, can we send 10, even 100 kilobits per second through this modem? Once again, breaking through those current paradigms that we're locked into by today's hardware radios. And one thing I'm particularly interested in is a low-cost TDMA repeater. Can we make a repeater, instead of being a box on a hill with duplexes and complex antenna arrangements, something like a HT in a different mode, where we simply press a button and suddenly it's being a repeater? Now that changes a lot of things that are that low cost and that easy to deploy. So the $100 TDMA repeater is another goal that I'd like to demonstrate with the SM2000. Not there yet, as I'll show where we're at, but we are getting close to one of the first goals there. Okay, I'm not a radio expert, but I did have a lot of fun working on this and designing it over the last 6 months. I'm the codec guy. I know there's many ways to build a radio. I just chose one that suited me at the time and those specific goals. A lot of other people do it better than me. I invite you to have a go. What this is really, this project's a vehicle for demonstrating some very bold goals. We're not trying to build the world's highest spec radio, so it may not suit everything that everyone wants to do at the moment, but we're trying to get those goals that I mentioned out there. In particular, get these new waveforms on the air and find out what we've got and work out our next steps. You know, should we be rebuilding this in a HT form factor? Does it need more power, less power, more CPU? I just feel that there's so much that's new here, we need to get something out there working before we plan the next steps. If you've got a design idea, that's great, but I'd much rather have you contribute. I get suggestions about how to spend my time on these projects every day via email, but what I really value is people helping me out, particular code contributions and things like that. Okay, so a little bit about the design. There's lots more information, schematics, block diagrams, all in the version control system that's available on the internet, the SM2000, just Google it. But basically it's a complete standalone 2-metre VHF radio. It's a super het design with 10.7 megahertz and 32 kilohertz IF. The 32 kilohertz IF is internal really to the signal processing, so we sample it further down to capture that IF. It's got a bunch of limiting amplifiers in the transmit receive chain, no AGC. I really like FSK. It's the first time I've really worked with FSK. I'm used to radios and modems that need linear modulation, like phase shift keying and analog, and they're very sensitive to distortions in the amplifier chains. FSK seem to bash it around a bunch of different ways, and we still get really good quality and really good performance out of it. So becoming a bit of a fan. It's got 1 watt of transmit power and filters that meet ACMA specs. So this is much more than your SDR dongle that doesn't have equal bandpass filters or doesn't transmit. This is a radio that you can actually use for real conversations legally and it will meet specs. It's been designed for that. There's a crystal filter at 10.7 megahertz, which provides a primary channel selectivity. At the heart of it is a microcontroller, the same one that we use for the little blue box that we've got all that experience on. Chosen really for that reason. We've got all that experience on it and a bunch of code runs and it does the job. A lot better, a lot of other processors, faster, better ones are coming out all the time. But as I said, the main aim is to demonstrate these waveforms on the air, not choose the absolute up-to-date microcontroller. These new microcontrollers, or this current crop, I guess we've been using this one for a few years, quite powerful. This is, I think, 168 megahertz router class processor, 1 mega flash, 128k of RAM.
Floating point.
Floating point is the critical fit, makes it easy to use. But they do have a 1500 page data sheet, and it takes a long time to even get a lead to bleed, you know, the first time you've used this thing. So once you've got a bit of experience on it, admittedly, I tend to just stick to it as a tool and move forward with that rather than, you know, looking at what's the next greatest chip that's come out there. So the microcontroller runs the whole FreeDV stack, the modem, protocol codec, plus all the user interface stuff. It's got a PGA 103 LNA, it's got quite a low noise figure. I think the overall noise figure in the radio is around 1 dB or 1.2 dB. We need that as we're shooting for this very low minimum detectable signal. The only thing it misses to make it a complete standalone radio is a user interface. It's got a USB port, and the idea is we'll hook up something via handlip to that. It does have some UI tools. It's got volume controls and push-to-talk buttons and LEDs and things, but it doesn't have an encoder or an LCD. I didn't really want to get into that. I'm here to get the waveforms and codecs working really, really well. User interfaces, a lot of other people do a lot better than me, so you know, we'll leave them to it. So where are we at with this project? It started in, I guess, the last quarter of last year. I started prototyping it on the bench, Manhattan style. Then the CAD people started working on it through the first 6 months of this year, and then we got the prototypes assembled. The first one we've got up here, I've hand assembled. We also had a couple built by my friend in China who manufactures the SM2000s. And then over the last probably 3 or 4 weeks, Brady and I have been bringing up the first prototype at the bench at my house and having a bit of fun with that. And that involves, you know, soldering bits together, putting code on the microcontroller. We hook the USB port up to our computers and we can upload chunks of data and have a look at the signals that are going into the thing. So a lot of it's based on the laptop. Write a lot of code on the laptop, download it, flash it. And then the sort of tools you've got these days are pretty good. I've got one of these low-end Regal spectrum analyzers for a couple of grand. They do a great job. And that lets us look at the transmitted signal and make sure things are working okay, debug the various parts of the board. We've made the board, as you can see, it's going round. It's sort of this sort of size. We've made it big on purpose. We use large surface mount components. I've never built a radio before, let alone one that's, you know, performs 10 dB better than anything else you can buy. So I had to make it easy to debug for my own benefit. It's got things like headers on the side of all the RF blocks, so we can 50 ohm terminations. We can plug in a spec amp and SIGGEN and just say test the crystal filter alone or the IF amp and characterise those. So it's really been made for prototyping. Once we've got the thing going and it works and we've met some of these goals, then we'll decide where we go next. You know, miniaturise the thing, or do we put some other product in a box? We're not really sure at this point. So we'll wait till we get it going for that point. Where we're at after a couple of weeks is we've got FSK transmission and reception going at the 10.7 megahertz IF point. So we can transmit signals, receive them. We're getting pretty reasonable performance. Brady, just 2 days ago, done a wonderful job at porting the 2400A mode to the microcontroller. He originally had that running on the PC, but when you put it on the microcontroller, a lot of things break. You run out of memory, you run out of CPU. You've got very little visibility because there's no console. It just doesn't work. and you have to make a lead blink or something like that to work out why. So Brady's done a fantastic job of just recently getting that running on the microcontroller. And that actually represents a huge chunk of the project. Probably 90% of the work on this project will be software, or has been. So to get that far, what's left is sort of analog debugging and loading up the VHF side. There's some work there, especially for me, because I'm new to radio, but certainly we've come a long way very quickly. So we'll demonstrate a little bit later on the 2400A RX working at the 10.7 megahertz IF. Where I was up to last time I looked at the hardware, some noise issues. We really need to make sure the noise is very low into the A to C converter to meet our MDS. Now we've got through a few of those and a few more to go, and lots more software that we need to run.
That's our line look.
Yeah.
Yep.
This would be my Manhattan-style prototype. Bit of a mess, but they always work better, don't they, when they look that way? Up the back we've got that's just an off-the-shelf development system for the little microcontroller I'm using. And that's the microcontroller in the middle there. So that's where the transmit and receive signals end up going. Off to this side's another project I worked on a few years ago. We're just using that because it has the LO chip that we're using. So they were strapped to the side of a bit of double-sided board, and yeah, just soldered away and hooked things up for a couple of months. This little board gets an MDS of minus 135 dBm.
What bandwidth?
1200 bits per second.
What's the receive bandwidth?
Sorry?
What's the receive bandwidth? Okay, so what's the noise bandwidth? 5K?
Well, I just do it on EVN North. So it was getting good low bit rate performance for 1200 bits per second FSK.
Yeah, it's going to be a 5K target, yeah.
So it would have been
All
around
right.
9 dB EVN North, but I don't actually work in the noise bandwidth because the modem takes care of that. Yeah, so that was receiving signals very low down, which gave me a bit of encouragement to move to the next stage. This is what we've got on the bench just here, which you're all welcome to have a look at later, but that's where we're at the moment. This was on the bench at home last week. So up the top here we have a bunch of power supplies. There's a 5-volt switcher that's been causing us all sorts of grief with noise, and some linear power supplies. The heart of the system is a little microcontroller. What have we got down here? Oh, USB interface, baseband amplifier, crystal filter, and mixers and things in here. And this is an IF amplifier there. Unloaded at this point is the VHF side. Not for any particular reason, it's just that we still need to get the noise down a little bit in here, in particular, before we'll reach our targets. And down here some 12-volt switching. The receive and transmit gets switched 12 volts, whether it's in transmit or receive mode. So things like these headers here, I'm not sure if you can see that clearly, but little 4-pin header that we can just hook a spectrum analyzer up to, and signal generator. There's another one on the other side of this block, so we can, if we hook one up here and hook one up here, we're testing the crystal filter section in isolation. If we hook one up here, then we're testing just the baseband amplifier on. So designed for test and for radio newbies like me. I spend my days peering at this sort of thing. This is a plot of a signal uploaded. We plug a USB cable into this thing, connect it up to the PC. We've got some software that takes a signal from the analog digital converter and just sticks it straight into the PC. We sample a chunk and then put it into, in this case I'm using Octave to plot the signals. So just sample it and plot it. This is what it looks like in the time domain. This is with no signal on the input. So what we've got down here, this is the frequency domain of the same signal, just the spectrum. We're sampling at 96 kilohertz, so it extends out to 48 kilohertz here. See these lines? So even with no signal, I was getting these lines, so it took us a little while to hunt those down. But by looking at how far apart they were 1200 hertz apart, which happens to be the interrupt service routine rate on the microcontroller. So the microcontroller is sort of sitting there, suddenly gets an interrupt, does a lot of work, goes to sleep again, and that's causing a chunk of power to be consumed through the power lines, which is getting into the analog side. I think the thing's got 150 odd, I forget how many dB gain, but anything that goes wrong with that sort of gain in it, you get something turn up at the analog digital converter. So anyway, hunted those down and then pushed these down a little bit with some power supply filtering, which gave us something like this. You can see these have now been pushed down 30 or 40 dB. They're still there on the edge a little bit. So this is with the minimum detectable signal going into it, something like 135 dBm, minus 135 dBm. And this trapezoidal shape is the crystal filter, amplifying the noise at the input of the radio through the IF chain. You can see how that falls off. That's just a regular FM radio type crystal filter that we use for adjacent channel selectivity. Now in the middle here, you can see these two tones sticking up. This was a 2 FSK signal, so 2 frequency shift keying. So those two tones are, I think, I can't remember if this is 1200 or 2400 apart, but I think it looks like about 1200. So they're your two tones, your 1 and your 0, coming through the signal there. And that was high enough to be received at, I think, about 1% bit error rate as a minimum detectable signal. And that's sort of how we debug. There's some things we can do with the analog test equipment, like the spec hand and signal generator, and other things we have to look at what the microcontroller is seeing. No, okay, I'm just letting a few wires go around and we'll see if we can get the demo running. Now, how this is working is Brady's sitting over there with a what's called a hack RF. It's a little USB device that can transmit and receive on quite a wide range. What do they go up to, Brady?
Gigahertz, 6 gigahertz.
Up to 6 gigahertz. So he's just using it as a transmitter, and he's got FreeDV software, FreeDV 2400 software on his PC that's generated the signal, and then he's playing that out like an RF sound card. So we're using that as the transmitter. And he's using a bit of software called GNU Radio to do the sort of convert it into a signal.
Frequency, yeah.
10.7.
10.7. This is just at the AF.
Yes, I should point out, this is just running at the IF, the 28 metre band. That's a fairly low power.
This is radio running KC9 EPA, Kilo Charlie 9 Tango Papa Alpha, Kilo Charlie 9 Tango Papa Alpha, recording some random voice derived through FreeDV. This is Radio Brian, KC9 EPA, Kilo Charlie 9 Tango Papa Alpha, Kilo Charlie 9 Tango Papa Alpha, recording some random voice derived through FreeDV.
Okay, so there you go. Thanks, Brady. Yeah, so fine work by Brady. As I mentioned, that represents a big chunk of the software working, which is the hard bit. Now, where do I put my laser point? Okay, this is what you'll all be doing shortly, instead of soldering things, programming software for SDR radio. So I thought I'd show you what it looks like. This code up here, this is a bit of C code. If you play around with Arduinos, it's not too similar, not too dissimilar. Here we're initializing the local oscillator chip, this line, and now down here we're programming in the frequency of the local oscillator chip. Now, as I mentioned, it's got an IF of 10.7 megahertz and then one of 32 kilohertz. So the local oscillator has to be set to the difference of the two. So here's 10.7 megahertz, and here's 32 kilohertz. And we just say, well, look, we want the difference of the two, so we subtract them in the C code. It turns out this particular local oscillator has a resolution of 0.01 times 100th of a hertz. So all the numbers we have to put in have to be hertz times 100. That's why there's a few more zeros on the end than you normally have. And then we tell the local oscillator chip that's the frequency we'd like. And away it goes. So if you had to tune that to another frequency, you'd get an input from handlib. You'd change that number and you'd change your tuning at the IF point. Although I guess you couldn't change it far on the IF point because your crystal filter wouldn't work, but there'll be another local oscillator that's very similar for the first mixer to tune the VHF. Now to use FreeDV, as I said, we've got an API or a library of FreeDV function calls. So, okay, look, I know I'm the codec guy and the modem guy. You guys don't have to worry about that now. You just have to include the library. And then you go FreeDV open and you say we want to use 2400A. And now, you can just start putting speech buffers in and getting modem buffers out and things like that. So that's sort of the starting point of using FreeDV. Down here we tell FreeDV we want to run at 96 kilohertz sample rate. So that's just a function call for that. And then there's a few other things we set. Down here is the frequency estimator limits. So When you receive the modem signal off the air, you're not exactly sure where those tones will be. They might be a few hundred hertz off because there'll be inaccuracies in various local oscillators and things like that. So it has a routine that automatically tunes to where the modem signal is. You don't have to turn a knob to tune it. And we're just saying, look, that modem is somewhere between 28 and 34 kilohertz, that modem signal, and it works it out for you and does the fine tuning for itself. So that's some of the initialisation code. There's a lot more code in there. I've cleaned it up, but I just wanted to show some key points and maybe remove some of the mystery about what we're doing. This is some code from the main loop. I'm missing, can't quite see that thing. There's a little thing in the way, but what I'm doing is just reading the switch. And there's a little switch, it's the PTT switch on the side, just like you have on any radio. And I get a value called PTT. Then I pass that to this function, which just says, this tells me where I'm applying 12 volts to. I'm applying 12 volts to the transmit or the receive side. So when I send PTT1 to this function, it powers up the transmit side. All 12 volts applied to the transmit side via some switch hardware on the board. When I send a 0, it sends 12 volts to the RX side. Down here we're sampling the analog to digital converter. So the receive signal's fed into an ADC called ADC1. And we just say, look, we'd like to get N samples, and I think N's, I don't know, it might be a couple of hundred, and stick them in this array called buffer. Then we pass it to the FreeDV RX function, buffer. So that's your modem signal going in, and out comes speech in another buffer. So that's the main FreeDV call for doing a FreeDV receive. So it's, you know, a bit like plugging cables in. One's got the modem signal, the other's got the speech out. We wanted to know how fast this software is running. So Brady's popped these little calls around it here which say, turn on the RT LED, turn off the RT LED. And that makes the RT LED blink and stay on for the amount of time that the microcontroller is executing this software. So if you put a Pro on the RT LED, you can tell how long it's taking to run that software. Down here there's another output we get from FreeDV, and that's if we've got sync. If there's no signal there, you won't have a valid synchronization. You probably don't want to play things out the speaker if you're not receiving anything. So that's how we tell if FreeDV thinks it's got a good, solid, synchronized signal. And if it does, we're lighting the error LED. I'm not sure why we're lighting the error LED when there's sync. Anyway, probably just a spare LED we had to use. Normally you'd light a sync LED or something like that, and you'd flash an error LED if it detects errors. So that's a little example of the code. Down here is DAC2 is the second digital to analog converter. That's the one we use for hooked up to the speaker. That's where we play the speech signal out. So modem tones come in, speech comes out that we play out of the speaker. So all this is saying is that if there's enough room in this speaker DAC to fit the samples we've got from FreeDV, then we'll write to the speaker DAC. So we're asking the API, how many samples have you got? Yeah, we've got enough room, so we write them, and that's how it goes out the DAC. So that's a major chunk of the main loop of the program, and how you can include FreeDV in an embedded program. This has been a real open and collaborative effort, and that's been part of the most fun for me. I get a bit bored sitting there doing open source software all day. I like working with people. Rick has been working with me for about 2 years now. He did the CAD work for the SM2000, PCB and the case. He's a retired engineer who lives in the east of the US and does some very fine job with the CAD work. Brady, who you've all met, he implemented the 2500 A and B modems in C and the protocol, and has also recently ported it to the SM2000. Neil, a friend of ours in Adelaide, who used to work for quite a famous radio company, has been doing RF PCB and has been invaluable in pointing out PCB layout issues. We tend to attract some really good guys for this work because it's pretty exciting and leading edge, and that's one of the exciting things for me. I put out an appeal, just like I did before, helped me with some code, and this guy responded. He sent me some driver code. Those local oscillator calls that I showed you before, Leon wrote those, and they worked almost first time. He just never met him, anything like that, he just sent me the code via email from around the world. So. And we've also had several RF engineers from commercial companies who wish to remain anonymous. But there's a lot of frustration in the commercial world with some of the things going on in the VHF SDR, in particular, closed source codecs. And these guys are only too happy to help initiatives in open radio. And they've been sending me a bunch of chips and helping me out with power amplifier design and things like that. So to summarise, we've got some new FreeDV modes, 2400A and B. 2400A is an optimal mode, the best we can design with what we know at the moment, that we believe will operate at least 10 dB lower signal levels than incumbent VHF, UHF modes. That is FM and first generation DV. FreeDV 2400B is a nod to existing radios. The difference is it will run through non-data port modems. Radios like your $40 HT with a average sort of performance. They use open codec, modem protocol, and now even the hardware is open. The SM2000's custom hardware, its primary aim is to demonstrate some of these advanced new modes that we're working on. And what's kind of cool to me, I guess, is that using open source we can build radios that hopefully will outperform current standards-based commercial radios that we're all sort of having to buy at the moment. And the great thing for me is that now that everything's open, there's no lockdown. You're not limited by what you want to do. It's getting easier. We're doing it with a relatively small team, with accessible test equipment. I'm sure some of you have got better test equipment than me who could be doing this. And as I've shown you with the way we've packaged up the software, it's possible for a lot of people to use this, the chunks that we've developed, such as the modem and codec. So thank you.
Questions for Dave?
The radio you're designing with the 2400A, will that receive the 2400B or no plans to do that?
I guess so. It's just an API port.
Yeah, there's no reason that it shouldn't be able to. It's just 2400B over FM. So that radio should be perfectly capable of receiving and transmitting FM as well as FSK.
We'd have to add software for an analog FM demodulator.
Yeah, there's nothing stopping us from doing that.
I'm just thinking of
just at the very
compatibility
beginning of the
with people
software.
that are just using the analog side of the world.
Yes,
filter them,
yes, it could do that,
Gary?
Yeah, my main interest is weak signal SSBs, like 2 millimeters or 7 centimeters. How does this stack up compared to, like you compared it to an FM transmission, but how does it stack up to a weak signal?
Not quite as good as SSB at this point.
What would be the difference?
That demo I showed you before would be about a 6 dB SNR signal for SSB.
Have you tried 700C, Gary?
No.
You can speak to that, though.
Yeah, we are doing some work in the HF area that we're pushing down towards the lower limits of SSB. Although HF is a different channel, the big problem is multipath.
And like a lot of people here have got experience with aircraft reflection, how does this stack up when you have multi-path signals, say, coming from an aircraft?
I'd have to look at the channel. I'm not familiar with that aircraft one, but I can talk to you about it later. We do a lot of multi-path on HF, for instance, fading, etc.
It's flat fading.
Is it flat fading? Okay, yeah. So, haven't done a lot of work with testing it with that sort of thing yet, but welcome to try.
Join the team.
Yeah.
Start playing.
Yeah.
No, the 700C is better than SSB on VHF. Yeah, it is.
The point is because it's open, we have control. We can adjust if it doesn't work for that channel. Now we can do something about it. The modem in particular and the codec. I went through this with HF. It wasn't working too well, so I changed the codec to make it work better for that channel. So they're the buttons we can push these days.
So from what Glenn was saying there, probably the best thing for VHF SSB was this 700C, was it?
The 700, I find the 700 is not always better than SSB, even at like 1 or 2 dB SSB signal noise. It's still better.
Yeah, so if you Google FreeDV 700 or 700C, look at my blog, there's some examples.
Okay, thank you.
Speech quality at various channels.
So I haven't been keeping up with the blog and stuff of late, but so it will run through the Windows GUI interface.
That's right.
With a digital to radio adapter. So you can download the GUI, load it up on your machine, and go through a digital interface into your SSB radio and give it a try. So you need, of course, 2 people to do that. But
Yeah, try the 700 mode. It doesn't sound too great, but you'll get your signal. You'll get a signal report through it.
Thank you.
And I'll be happy to work with you on that VHF.
Thank you.
Thank you for your contact.
Yeah, okay, I'll speak up.
Probably a simple question for Brady. How big was the code on the SM32? What did it come down to? 300k or something?
That's a good question. I think it was around 300K. Right now, we're not getting close to hitting the limit, so I haven't been keeping up exactly where it is. Most of that is actually in the, I'm pretty sure it's in the code books for the codec itself.
Yeah.
I mean, the meat of the FSK modem is only about 200 or 300 lines of C.
Okay.
So it's really not a very complicated modem if you get into it compared to like the PSK or the FDM ones that David's been working on for 1600 and 700.
That's good.
Yeah.
We keep banging into runtime RAM limitations.
Okay, yes.
We've never got close to the
This
flash.
is like, okay, so
Yeah,
it's a run error.
that's usually where the optimization work lies.
Yeah, okay.
Any more questions? Sounds like plenty of fun to go and play with. So thank you very much, David, and Brady.